Okay, welcome to lecture. Give me 1 second. Just gotta kind of arrange a couple of things. And we'll get started where we left off last time, talking about equilibrium. So again, we'll get started in just a minute here. Just give me a second. Okay, so we're going to continue on here in chapter 6. We're going to lecture for a little bit, and as we talked about last time as well, um, we'll be stopping a little bit early here, and that should free up your time to then take the quiz, which will start somewhere around 8:30, and that probably should give you enough time to kind of finish it, so forth. So again, the quiz will be done on Canvas, like we've done everything else. And again, we'll stop lecture a little bit early, and you can take the quiz starting at 8:30. Again, that should free up that time for you to do so. So, like usual, if you do have questions, feel free to ask them as we're going along here. Again, even if we've sort of moved on from that page or whatever it may be, feel free to come and ask them, and we'll go back and make sure we get everybody's question. So where we left off last time was we were talking about equilibrium and chemical equilibrium. And as we talked about at the end last time, chemical equilibrium is for a specific type of reaction. And that's a reaction where we have basically a reversible reaction. So in a reversible reaction, like we talked about at the end of last time, we have a forward direction, which means that reaction will proceed from the reactants to the products like normal. And we also have, at some point, once you start building up some products, the reverse reaction will take place. And that is when the products will actually come back together and start to form some of the reactants. So you can think of sort of a reversible reaction as a two-way street. There's a forward direction, there's a reverse direction. And when we do reach chemical equilibrium, again, as we talked about last time, it does not necessarily mean that you have the exact same amount of reactants and products, not exact same concentration or anything of that nature. What it really does mean when we reach chemical equilibrium, again, is that the rate at which the forward reaction is happening, going from reactants to products, will equal the rate at which the reverse reaction will be happening as the products go back to the reactants. So basically, when we reach chemical equilibrium, there's basically a back and forth happening, and they happen, as it shows here, at the same rate. And essentially, what that means is if they happen at the same rate going forward and going backwards in terms of that reaction, essentially what will happen in terms of sort of the concentrations of everybody that's there is they will sort of lock themselves into place. So whatever concentrations your reactants are at that moment, whatever concentration your products are at that moment, because it's going back and forth at the same rate, nothing will sort of change in terms of their concentration. They sort of get locked into there. So like the example up on top in the middle, if we reach chemical equilibrium and we have 4 of the first guy and 2 of the second guy, 3 of our product and 4 of our other guy, just made up numbers there. What that means is they will be able to maintain those concentrations at chemical equilibrium, because just as fast as it goes to the products, it will come back to the reactants. And again, on the sort of the big picture, if you're looking at something that's reached equilibrium, say in a beaker or something like that, it may appear to you that nothing much is happening. But if you were to sort of super zoom in and sort of see what's happening on the molecular level, there's a lot of activity going in both directions. So there's a lot of activity, stuff going this way and just as much coming this way. But again, on sort of the big picture, if you just kind of looked at it, it may not appear that much is happening, for example, in that beaker. But again, if you sort of super zoomed in, you see all this activity that's occurring to maintain that equilibrium. So when we have a reversible reaction like this, and we have an equation such as this here, this generic equation, A plus B goes to C plus D. Again, we know it's a reversible reaction because of the arrows that are heading in both directions. That's a really big key, that it's a reversible reaction that's going to reach equilibrium, is those arrows. And there's one way we could sort of describe sort of this equilibrium, and this is with what is known as capital K. And capital K is what is known as the equilibrium constant. So capital K is the equilibrium constant. And the way we calculate that is the concentration of our products over the concentration of our reactants. When we talk about concentration, this is usually what means molarity, which is moles per liter, which we'll get into shortly, I think. But that's basically what the little brackets mean. It means concentration. And we do take actually the coefficients from the balanced equation, and they actually become our exponents when we do that calculation. So we take basically the concentration of our products, we divide it by the concentration of our reactants, and that will give us this value of K. And this value of K is kind of important in the sense that it will tell us that when we reach equilibrium, it will actually give us a value of, in the sense of, do we mainly have products there when we reach equilibrium? Do we mainly have reactants there when we reach equilibrium? So when we do calculate this, and I don't know if we're going to do too many calculations that involve this, it's actually just a number K. So K is typically just a number that you get. There's actually usually no units associated with K. You kind of do the products over the reactants, the concentrations, gives you this number. And the reason it's able to kind of tell us, when we reach equilibrium, do we mainly have reactants or products, is if we have a relatively large value for K, what that means is we would have to have mainly products when we reach equilibrium. And that's because a large value on top divided by a small value on the bottom would give us a large value for K. And vice versa, if we had a small value of K, as we will see, that means when we reach equilibrium, we mainly should have reactants that are present. For the same logical way here, math speaking, that would mean that we have a small number on top and a larger number on the bottom. And that's going to give us a smaller number. So the value of K itself, which is usually just a number, like I said, no units associated with it, you could actually use it to figure out that when this reaction reaches equilibrium, do you mainly have reactants present? Do you mainly have products present? Just based on that number. And so, for example, here is a real equation here. And in this equation here, again, we can identify it as a reversible reaction when we see these arrows heading in both directions. And we're going to do our equilibrium constant, which is K. So it's going to be our products, which is this side. So this is the concentration of NO. The coefficient here for NO is 2. So that is where this 2 comes from. So we take the concentration of NO squared, and then we would divide it by our reactants. So we have our N2. The coefficient here is 1, not written. And that's why there's nothing here. This is technically 1, right? Same thing here. This is O2. And same deal. The coefficient here is 1. And just like normal, we don't usually write the 1, but technically those would be 1s right there on the bottom. And if we actually had the numbers, we would essentially just need to basically plug it in there, and you could get an actual value for this sort of equation. So We take the concentration of our products, we divide it by the concentration of our reactants. Again, we use the coefficients as the exponents, and that will give us the equilibrium constant. The equilibrium constant is a constant for a specific temperature. So the K value is constant at a specific temperature, which essentially means if you keep the temperature at the same sort of value, so say you kept it at 25 degrees Celsius throughout an entire experiment, if you started with different amounts of N2 and O2 in this particular reaction, it would come to equilibrium in the same proportion, and you would get the same equilibrium constant value, regardless if you started, say, the first time with 5 of the N2 and 2 of the O2, or if you started with 4 of the N2 the next time and 3 of the O2. When it does come to equilibrium, as long as you don't change the temperature, the value of K will remain the same. So temperature is really the only thing that will actually affect the value of K. It will actually change the numerical value of it for a reaction if you change the temperature. So for example, if you go from 25 degrees Celsius to 50 degrees Celsius, the value of K at 25 degrees Celsius for this reaction and the value of K at 50 degrees Celsius will be different values. But once you get to 50 degrees Celsius and you keep the temperature at 50 degrees Celsius and you start with a variety of amounts of reactants or products, it will always remain the same number at 50 degrees Celsius until perhaps you change the temperature again to something else. So it is constant over a specific temperature. Once you change that temperature, the value of K will change between the two temperatures. But again, once you get to, say, the new temperature and you don't change it anymore, it will still remain the same. So again, what that again means is K at, say, 25 degrees Celsius will be different than K at 50 degrees Celsius. But at 25 degrees Celsius, the K value will remain the same all the way through, even if you change the concentrations of everybody. And if you get to 50 degrees Celsius and you keep it at 50 degrees Celsius, it will remain the same, even if you change the concentrations of everybody. Basically, the proportion of products to reactants will remain the same. Now, this value of K that tells us if we have a large value, do we mainly have products? Do we have a small value? Do we mainly have reactants? So what's sort of considered large or small? A large value of K is that big number of 1, is basically 1. So anything above 1 is considered a large value of K. And that would tell you, like it's highlighted over here, that just mathematically speaking, you would have more products. Anything that's considered a small value of K is less than 1. Again, that 1 is that big number there. So kind of less than 1. And that would mean the opposite, like we were just talking about in terms of the math. In order to get a small number, we would have to have more reactants than products. And again, on the top there, in order to get a larger number, you would have to have more products than reactants. So when K is around 1, you have kind of a equal amount or good probability of having both reactants and products there. Again, just mathematically speaking, in order to get our products and reactants equal to 1, they pretty much need to be the same number on top and bottom when you divide it, right? Will give you 1. So typically, if we do have sort of a K value around 1, usually that means we have a good amount of getting the same amount of reactants and products there when the reaction reaches equilibrium. So again, when the reaction reaches equilibrium, we're talking about the rate of that forward reaction versus the rate of that reverse reaction. Now, if you do see a K value like this is 2.9 times 10 to the 82. That is 82 places in that direction, and put some zeros. That is a ginormous number. That's a big number. And a K value of that big pretty much tells you that everybody is pretty much heading in that direction, heading towards products. That's almost like a one-way street um, with a K value that's that large. So because of that, obviously products would be favored here. Definitely that is way above one, and almost to the point where you could almost consider this reaction a one-way street, because pretty much everybody is definitely heading towards the products in this case, because that is such a large value of K. So for our purposes, like I said, I don't think we'll be calculating K too much, actual values, but if you do see a value of K, it does give you some information about that reaction. It gives you information about, sort of what's happening when this reaction reaches equilibrium. Again, just to review what we've just been talking about, large value of K, which is considered above one, would mean that we should have products when that reaches equilibrium. It should be lying to the right-hand side of the arrow. When we have a small value of K, which is usually less than one, so some type of K value that has like a negative exponent, like 1 times 10 to the minus 5 or something like that, that means the opposite is true. When that reaches equilibrium, not much has gone towards the product side. We're pretty much hanging out on the reactant side, and the equilibrium would sort of lie to the left. And again, if we're sort of around one, that would imply that we have kind of equal amounts or similar amounts of reactants and products at that point when we do reach equilibrium. And this right here is just an example. If you were actually given the equilibrium constants for a particular reaction, you could actually calculate K. So just to show you what the calculation looks like, we would write our equilibrium expression here, which is our product. So it would be the concentration of A, B, which is our products. We would also square it here, again, because of the coefficient that we see. We would divide it by our reactants, which in this case is A2. Coefficient here is 1, so that's why there's nothing written up here. Like normal, it applies 1 times our B2, where also the coefficient is 1, which is why there's nothing written here. Now, if they give you these concentrations, these would be the equilibrium concentrations, and you would need the equilibrium concentrations of each of these guys to go into the equilibrium constant. So in order to go into the equilibrium constant and calculate K, you would have to have the equilibrium concentrations given to you, which for anything for us would be given to you because to calculate it is outside of this class. We don't really talk about that. If you take 1B or whatever that class is called, you will do it at that point. So if we plug the numbers in, AB's concentration is 0.5 molar, which is what the big M stands for. It's a concentration. We would divide it by, and we would want to square it. We would divide it by our A2, which was 0.25, and our B2, which was 0.25 as well. And if we put those numbers in, taking 0.5 squared divided by 0.25 divided by 0.25 gets us a K value of 4, I believe. Try that again here. Divided by 0.25 and by 0.25. Gets us a K value of 4. Again, when you do calculate K, is just a number, no units associated with it. This also should tell us that this is a large value of K, again, above 1, which means when we reach equilibrium, we would expect the equilibrium to be headed in this direction, and we would expect mainly products to be there, again, because of the large value of K that we see in this case. Any questions on that there? Again, if you do have questions, feel free to ask, and we'll get to them. hopefully that's what they got. There it is. Yeah. And again, like we see here, it is no units associated with it, so you don't have to worry about units. And again, like I said, I don't know how much K calculating will do. If we did, it would be something like this, where you just kind of write the expression and plug in the values and stuff like that. All right. So really where this leads us into in terms of equilibrium and sort of reversible reactions, really for our purposes in this class, is to talk about this idea of what's known as Le Chatelier's principle. And Le Chatelier's principle is basically this idea that you have a system that's at equilibrium, and then what you do to it is you add a stress to it. And basically what that's going to do is mess up the equilibrium. But this reaction is once again going to want to try to get back to an equilibrium state. So it'll once again try to get back to that equilibrium state. And in order to do that, there's usually three things that perhaps would happen. It would sometimes need to shift to the right, which basically means that you need to make more products to allow it to once again reach equilibrium. It may cause that reaction to shift to the left, which means in order for it to reach equilibrium, you would actually need to make more reactants. And the third option that comes out with Le Chatelier's principle is actually really no shift at all. There's certain cases where no matter what happens or what you do to it, you pretty much will cause no change. So there'll be no change that will occur. So what are stresses that we can do to a system? It's these guys right here. These are common stresses that you can basically add to this sort of system. You could do concentration changes. What that essentially means in terms of concentration, you have two options. You could either add more of something, or you could remove. And each of those sort of situations will cause a certain effect usually to occur. Again, it will cause it either to shift to the right, cause it to shift to the left, or may cause no change. Temperature as well, you could pretty much do the same thing. You could either increase the temperature, which is like adding, or you can decrease the temperature, which is like removing. And the third thing that very commonly happens in Le Chatelier's principle is you could affect the pressure. And when we talk about pressure, we're really talking about gases here. And when we talk about pressure and volume are related to each other. And again, you can either increase the pressure or you can decrease the pressure of a situation or an equilibrium that basically involves gases. So each of these things will have sort of an effect on the overall equilibrium. It usually, again, will sort of mess up the equilibrium, not allow it to go back and forth at the same rate, but it will want to naturally sort of get back to that equilibrium. So again, it sort of self-adjusts by either making more reactants, making more products to go in one direction or the other to once again reach equilibrium. So let's take a look at each of these and sort of talk about what happens with them. So really the first thing that we're going to talk about is a change in concentration. And in a change in concentration, as I mentioned before, there really is two things that you can do. You can either add more or remove. So when we talk about concentration, we can add more. And when we add, a very kind of simple thing happens. When we add, the equilibrium will shift away from where we added. And when we talk about that, in reality, everybody's in the beaker or the container to begin with. But when we look at the chemical equation, when we talk about adding more, maybe we're adding more on the left-hand side of the equation, maybe we're adding more on the right-hand side of the equation. And again, it shifts away from the side where we added it. AA is a good way to remember that. when you remove something, it does the opposite. It actually will shift towards the side you removed. And when we add more concentration, that's pretty easy to determine how you do that. If you need to, you go to the shelf, you pick up the reagent or whatever it is, and you dump it into your kind of solution or whatever it may be. And that's a very easy way to sort of remove something. Now, I'm sorry, to add something. Now, to remove something, the one way or two ways that we can kind of remove something is by making a precipitate, basically a solid, or you can make like a liquid. Another way, most commonly the liquid we're talking about is like the formation of water. You can't really see necessarily when you make water, but that's usually making a liquid. When you make a solid, you can see it obviously when you add something. You obviously, if you have a solution, can't reach in with your hands. You shouldn't do that, obviously, and pull out anything from that solution. But this is a way you can sort of pull things out of the solution. And why that's important is just going back for a second. When we talk about writing our equilibrium constant values, our K that we did, which is our products divided by our reactants, there actually is two things that we typically do not include. Into this expression. And those two things are things that are solid, are things that are liquids. So when we actually do write those K expressions like we sort of did in the last couple of problems, there's actually two things that we do not include, which are solids and liquids. Yeah, so we're going to talk about the relationship in terms of pressure and volume just a second when we get there, but there is definitely a relationship between those two, and we'll talk about it when we get to that one in just a second. Now, things like solid and liquid aren't involved in the equilibrium, again, because if you think about it, if you have something that's a solid, it's just kind of sitting there, say on the bottom of the beaker and so forth. It's not really participating. Things that are pure liquids have concentrations that basically remain constant throughout. So really, when we do write something like Q, RK here, we basically only include things that have the aqueous symbol, or things that have the gas symbol, or the guys that basically will go into that expression. So this is one way that we can kind of remove something from an equilibrium where it will, not have a tremendous effect on the equilibrium constant, but still do the aspect of removing something. So when we think about concentration, you could think about it as sort of the basic sort of here, let's see. So let's say we had my guys on the teeter-totters here, nice little stick figure action going on. And we'll say the guy on the left here is our reactants. The guy on the right is our products. And at this point, they're at equilibrium. And if, let's say, somebody hopped on the right-hand side, what would happen in this case is you would end up with a couple of guys on this side. This guy over here would be a little sad. He's now in the air. So since we added to our right-hand side, what we need to do to fix this is put more people on the left-hand side. So to fix that, the equilibrium is going to shift to the left, away from the side we added it from. And once again, this guy will come back to chemical equilibrium. And it'll come back to equilibrium. So again, when we add, it will shift away from the side we added to, and vice versa. If we have this guy here and the guy on the right decides to jump off, when the guy on the right decides to jump off, we would get this sort of situation. Now you can see we removed things from the right-hand side. In order to fix it, we need to put more people on the right-hand side. So it's going to shift to the right. And again, this guy will be able to come back to equilibrium at this point, and everybody would be happy again. So when we add, it shifts away. When we remove, it goes towards it. So for example, if we added more CO, like the big arrow there basically denotes, when we add more CO, CO is on the left-hand side of the equation. So it's going to cause the equilibrium to shift away from the side we added it to. And what that means in terms of sort of concentrations, is and the O2 will start to decrease, as it says here, because the reaction is heading to the right. The amount of CO2 should start to increase in that case. Again, more O2 would go down, CO2 will go up. CO would actually go up a little bit because you added it, and then would come back down. Now, in this case, if I added more CO2, again, CO2 would be on the right-hand side. When we add, it should shift away, which means this equilibrium should shift to the left-hand side. And when it shifts to the left, that means that we should be making more of both of these guys here. The CO and the O2 guys should start to increase. Now, if in this case I removed O2, O2 is on the left-hand side. When we remove it, it actually will go towards the side that we removed it from. So in this case, that would cause the equilibrium to shift to the left as well. Again, shifting towards the side we removed it from. If we remove CO2 in this case, again, CO2 would be on our product side, on the right-hand side. And again, when we remove it, it would go towards the side we removed it from. So we would expect the shift in equilibrium to go to the right in this case. So add away, remove goes towards it. And when we talk about sort of left and right, you could use the equation to help you sort of visualize left and right in terms of which way it is shifting. Any questions on that there? So again, as we were just talking about here, if we increased our CO2, again, going to shift away, so should shift to equilibrium, like we talked about, to the left, which means, again, the O2 concentration should increase. The amount of CO will also increase as well because of that shift. And here again is that removal. We look at this equation here. If we remove H2O in this equation, again, when we remove H2O, is going to go towards it. So H2O is on the right-hand side. We would expect the equilibrium to shift to the right. And that means that we should be making more of this guy, less of this guy as we go that way. Now, if I added more ethanol, ethanol is on the left-hand side. So when we add, it will go away, should also shift the equilibrium to the right. If I added more of this guy right here, this guy is on the left, the right-hand side of the arrow. So when we add it, we would expect it to go away from it and shift to the left. So again, you can basically use the equation as sort of a visual reference for shifting to the left, shifting to the right. And obviously, if we shift to the right, we're going to make more products. and we would have less of these guys on the reactant side, and vice versa. If we shifted to the reactant side, we would make more reactants and we would start to lose some of our products again, because in this case, what we're almost doing when we sort of adjust the concentrations or add more concentration, add less concentration, we're essentially causing this reaction to almost behave in a one-way street. So when we cause it to shift to the right, we're essentially causing it to everybody for a short period of time head in one direction, which means we should be decreasing our reactants, increasing our products, and vice versa. If we cause it to shift to the left for a temporary portion of time, it's almost acting in a one-way direction where we would expect an increase in our reactants and a decrease in our products. So the other stress that we also talked about, or we'll talk about here, is temperature. And temperature behaves the same as concentration, which means if you increase the temperature, that's like adding, and it will shift away. And if you decrease the temperature, that is like removing, and it will shift towards it. So when we talk about sort of away and towards in terms of energy, it is all dependent on whether that reaction is exothermic, which means heat and energy is released, and if you remember when we talked about delta H, that is a negative value, which implies an exothermic reaction. When we write an exothermic reaction and we want to put heat and energy in it, because it's being released, heat and energy is thought of as being a product. So it would be on the product side. And that is opposite if we have a endothermic reaction where heat and energy is absorbed. And the delta H value for those guys is a positive number to imply that. And in this case, that means heat and energy is thought of as a reactant. So it would be on our reactant side is how you think about it. So if we increase the temperature in an endothermic reaction, it would be like adding heat and energy to the reactant side. And when we would, it would shift away from it towards the products. And vice versa, if we lower the temperature in an endothermic reaction, it would be like removing heat and energy from the reactant side, which means the equilibrium would shift towards the reactants. It's opposite over here for exothermic. If we increase the temperature of an exothermic reaction, that means heat and energy on the product side is going to increase and it will shift away from it, which means it would shift towards the reactant side. And if we lower the temperature, which is like removing temperature and heat, which because it's on the product side, it would actually shift towards the products. So when we think about changing the temperature and its effect on equilibrium, we want to think about it in the sense of, is it exothermic or endothermic? And very much like that reaction that you see in the screen here, this is oftentimes how that is displayed to you with the delta H value. The number here doesn't really matter. The important part is it's positive. That tells us that this reaction is endothermic, which means if we wrote the heat and energy into this equation, it would be found on the reactant side. So in this case, if I increase the temperature in this case, that would mean adding more heat and energy on our reactant side. And when we add, it will shift away and we would expect the products to be made in this case. And vice versa, if I lowered the temperature in this reaction above, That would be like removing the heat and energy on our reactant side. And when we remove it, it goes towards the side we removed it to. It should shift to the left in that case. If we added O2 to this reaction, again, if we added O2, it's on the left-hand side, add, it goes away. We would expect the equilibrium to shift to the right. If I removed NO in this case, again, NO is over here on the right-hand side. When we remove something like we talked about previously, it goes towards the side we removed it from. So again, temperature works the same way. If you increase it, it goes away or added. If you decrease it, it goes towards it. And really the most important thing to figure out when you're trying to determine temperature changes and equilibrium is what type of reaction you're dealing with. Is it exothermic or endothermic? Any questions on temperature there? And we're going to get to that pressure and volume in just a second here. So here's another example. Again, if we have this reaction, numbers not important, but what we see for the delta H is it's negative, which automatically tells us it's exothermic. So again, if we put that heat or energy in, it would go on the product side. So in this particular reaction, if we increase the temperature, it would be like adding more products. It's going to cause the equilibrium to shift away, and it would go towards the reactant side. And if we decrease the temperature here, it would be like removing this side, and it would go towards it, and it would shift to the right. If I removed N2 in this case, just to practice a couple other things, if I removed N2, again, N2 is on the left-hand side. When we remove it, goes towards. We would expect it to shift to the left. If I added NH3, like we see here, NH3 is on the right-hand side. When I add, it goes away, would also cause this guy to shift to the left. Any questions on those there? Okay, so I think now we're going to get hopefully to your question earlier about pressure. Now, pressure and volume are related to each other, which we'll talk about in the next chapter, but basically they're related to each other through a gas law known as Boyles Law. And basically the relationship between pressure and volume is as the pressure increases, the volume will decrease. So it's basically an inverse relationship between pressure and volume, and vice versa. If the pressure goes down, the volume goes up. And when we talk about pressure, that should make you think of gases. And that is what we deal with in sort of Chatliers Principle when we talk about that pressure, is we deal with basically gases. So the easy way to remember this is really, I think, for the volume relationship. If you increase the pressure, the volume will go down. And when we have a kind of smaller volume, what we want to do is basically end up with less gas molecules. Less gas molecules will help fix the change that occurred. The change that's occurring here is essentially the pressure starting to rise, which means if we have the same amount of gas molecules or more gas molecules, the pressure will continue to rise because there's nowhere for them to go in this small space. There's going to be lots of collisions occurring, causing the pressure to continue to increase. But if we shift down to the side that has less gas molecules in that small volume, what that's going to do is cause less collisions. It's going to take longer for those collisions to occur. And because the pressure started to go up, that should kind of bring the pressure back down. And the same thing would be true in the opposite effect. If the pressure goes down, that means the volume goes up, which means in this bigger area, we actually need more gas molecules. So the idea here is the change that's occurring is the pressure is starting to come down. we essentially want to bring the pressure back up. So in order to do that, when we put more gas molecules in this bigger area, that is going to increase the rate of collisions and cause the pressure to kind of come back to where it was-ish in terms of equilibrium. So in terms of shifting to the left, shifting to the right, in this type of situation, it is dependent on the reaction that you're looking at. So what you want to look at is the states. You want to look at everything that is gas molecules, and you can use the coefficients to add up how many you have. Coefficient here is 1. Coefficient here is 3. So on the left-hand side, in this example, we have 4 total gas molecules. On the right-hand side, the coefficient is 2, which means on the right-hand side, we have 2 gas molecules. So if I lowered the pressure in this case, what that means is the pressure is going to go down, but the volume will go up. And in that case, we need more gas molecules. So in this particular example, it would actually shift to the left, to the side that has more gas molecules. Opposite would occur if you increase the pressure. When you increase the pressure, the volume will go down. So in that case, we need less gas molecules, which in this particular reaction is to the right. I personally think about pressure and volume because they are related to each other. I think about it in the sense of volume. It's a good way to remember it. Small volume, less gases. Larger volume, more gas molecules. So sometimes it's easier to kind of think about it in terms of the volume aspect and then know how pressure is tied to that, because they oftentimes are asked kind of similarly here to tie both of these guys together. If we said hypothetically that the delta H of this reaction was positive, and just making that up, that would tell us that this is a endothermic reaction, which means heat would be over here. And if I decrease the temperature, that would mean that we would be removing on the left-hand side, and that would cause the equilibrium to shift to the left in this case. Again, if I added more NH3, we would be adding to the right-hand side, going to shift away, also would cause it to shift to the left. Let's see if we have another example of pressure and volume here. So this was the same one, decreasing the pressure. Again, decreasing the pressure means that the volume is increasing. Again, larger volume, more gas molecules, why we're again shifting to the left in this case. All right. So here's just a summary table of some of the stuff that we talked about, which is, again, if we add concentration, it shifts away. If we remove concentration, it goes towards it. Temperature works the same way. So you need to determine whether it's endothermic or exothermic. Again, if it's exothermic, the heat would be considered a product. If it's endothermic, the heat would be considered a reactant. And pressure really is related to volume. Again, larger pressure, smaller volume, less gas molecules, whichever side that is. And less pressure, larger volume, more gas molecules. Again, will shift to whichever side that is, and it is reaction dependent. The last thing that sometimes will affect a equilibrium is a catalyst. And a catalyst, as we talked about, I think in this chapter earlier, is really just there to speed up a chemical reaction. And it's not a reactant or a product, and it will actually cause no change in the equilibrium. So if you add a catalyst to it, it will not basically affect anything. Okay, good. It will not affect anything in terms of the equilibrium, have no change. So let's just take a look at one last one here to finish up. Let's just say we randomly had 3A, that's gas molecules, plus 4Bs that are also gas molecules. Go to 2 C's that are gas molecules, and we'll say the delta H in this case is negative. All right, so in this case, let's do some examples. So if we added more A, again, if we added more A, A is on the left-hand side, add away and not hit the button. Let's go that way. So it should go away from the A, which is on the left, which means it will shift to the right in this case. If we decrease the volume, remember volume and pressure related. So when we decrease the volume, the pressure should increase. But really when we think about volume, that is a smaller volume, which means we need less gas molecules in that smaller volume. Left-hand side, there's a grand total of 7 gas molecules. Each of those are G's. On the right-hand side, there's 2 gas molecules, which means in this case, we would expect it to shift to the right. If I removed B, remove some of B, B is on the left-hand side, so when we remove it goes towards, so it should shift to the left. If I increase the temperature, this case, the delta H is negative, which means it's exothermic, which means heat would be on a product side in this case. And when I increase the temperature, it works like concentration. So we're increasing the product side, which is the right-hand side, should shift away, should go to the left. If I add a catalyst, it will cause no change. By the way, other things that will cause no change is if you add something like a noble gas. Noble gases are chemically inert. They will typically cause no change to occur. And another way that you could actually get a no change, for example, let's just say we had 2A that is gas, goes to 2B that's gas. And if we had this equilibrium and I decrease the pressure, we would want an increase in volume and more gas molecules. But in this case, there's 2 on the left, 2 on the right. That's a tie. So there is no more or less in terms of that. And that would actually cause a no change in that situation as well. So there are a few places where you can get sort of a no change to occur. And that would be another example. If you sort of the pressure and volume and there is no more or less in terms of gas molecules, then it would be no change. Any questions on Le Chatelier's principle? That also should wrap up chapter 6 in just about the right amount of time. So that's good. Any questions on that? Okay, so we're going to stop lecture now. The quiz should be open right about now. The quiz will be taken just like everything else that we've done on Canvas there. You will basically do your answers. You'll have a certain amount of time to take it. So make sure that you do take it. I think you have 45 minutes, which should be plenty of time, I think, to take it. In this particular quiz, just so you know, there is an assignment to upload your work, but there really is no work to upload, I don't think. So the only thing that you would need to upload is the academic honesty agreement if you did not sign the electronic one. If you signed the electronic one, you're good. You don't have to really upload anything for this quiz. There's really no work because it's basically nomenclature. So, you just want to type it in. When you do read the quiz and go through the quiz, make sure that you do follow the instructions in terms of how to enter things like the formulas and the names and stuff like that, and try to follow those things so nothing gets sort of marked wrong by the computer. I don't have to go back and change a whole bunch of things. So make sure you take a moment there, read the instructions on each of the questions, and make sure that you answer them. All right, any other questions on anything? All right, so we'll stop there. That should free up plenty of time, hopefully, to take the quiz. So go take it now. Again, it's only available for a very short period of time right about now. But you should have plenty of time if you sort of start sort of immediately-ish. You don't have to start like right this second, but in the next, 10, 15 minutes, you probably should have enough time, to finish and all that good stuff. Before, if you have lab today, for example, you should probably be able to knock it out. All right, other than that, have a good weekend. We will continue lecturing on Monday on chapter 7. Remember, 1 week from today is exam number 2, I guess it would be. All right, have a good one. Good luck on your quiz. I will see you next time. Thank you, you too.